Okay, the recorder started. Okay, we're recording. Good afternoon, dear student, and welcome to this first class of numerical method 2. It's a pleasure to have you once again in this lecture. And we are going to spend the rest of the semester together, be it online or face-to-face. The health condition of the country will determine whether we'll meet online or we have blended face-to-face online or fully online. No one knows. So as the situation will prevail, they will know exactly what to do. The institution will tell us exactly the conduct to take. All right. So numerical method 2, I uploaded the course outline. Please, I encourage you to download it and go through the syllabus. So let me do that. Since course outline, I did not even open the course outline, but let me try to do that so that we'll quickly go through the course outline together for you to have an idea of what we are going to cover during the course of this semester. Let me open. I hope you downloaded the course outline. Explorer. Course outline. Which one is this? Okay, numerical. Great. This is the course outline. Let me open it. Great. Having opened, now let me share it with you. Course outline. Oh no, not that one. Okay, but the course outline is not showing. It is not showing there, but let me do this. Okay, let me do this. No, not it. Not the thing. Recent. Let's see, because I can really do this. No, if I get desktop. Now from desktop, I can go to, where is that? I want the link. Oh, it's looking for something, but that's not what I want there. The link, I don't see those links. What's there? That's this one. Oof. Okay, sorry for the time that it's taking, but this thing is it's not showing. I opened the course outline, but it's not showing here in the list. So it's difficult for me to. Okay, anyway, I will just share the actual. Let me share. Okay, chapter 1. For us not to waste too much time. Okay, so this is as you can see here. Okay. As you can see here, you have an idea of the course outline. Anyway, the course outline has been updated, uploaded. You can download and go through. So the first part of the program is about approximation theory. You can see that it's divided into 3 parts, right? The first part is approximation theory and application, and then you have numerical integration, and finally, eigenvalues and eigenvectors. So those are the 3 main components of the module. So the first component, or the first part, which is approximation theory, is about approximating a function, right? Let's say, for instance, you have a set of data points, and you want to represent that set of data points using a function. There are many ways that the data point can be approximated. And the purpose of, and the main heading for that is approximation theory. So you have the least square method, which you know already from MMO, mathematical modeling. In mathematical modeling, you tackle the least square method. So least square method is, you have a set of data points, you want to approximate it, right? There are many ways. In the least square method, the purpose of the least square method is just to minimize the error of the approximation compared to the, okay, thank God we did the interpolation. Yeah, interpolating polynomial, we did that. Yeah, last semester. Okay, when it comes to interpolating polynomial, if you recall well, you will see that when it comes to interpolating polynomial, the error is really large in the sense that if you have n plus 1 set of data points, and you want to approximate using a polynomial, the degree of your polynomial will be n. And if n is large, let's say from 10 upwards, your polynomial becomes, there is uncertainty in the sense that the error at the endpoint is very large. And there is a phenomenon called the wrong phenomenon. I think I showed, I illustrated through the graph. We didn't go in the depth in the theory. We didn't go into the theory of a wrong phenomenon, but I only show you some graph for you to see that at the endpoint there are wide oscillation, which makes the error very large. And for that purpose, I think I indicated that polynomial interpolation are not good to approximate functions. This is something you should bear in mind, even if it was not written formally, but bear in mind, when it comes to approximating a function, polynomials are not good at all. Polynomial, when I say polynomial, interpolating polynomial, are only good when it comes to numerical integration, as we will see later on. They are good for that numerical integration, numerical differentiation. You can use polynomial or interpolating polynomial. But if you want to approximate a function, don't use interpolating polynomial because they are not good at all. An improvement to that, you can use piecewise interpolating polynomial, those one gives a very good accurate result compared to direct interpolating polynomial. I will try to make myself clear. Let me share a window. Let me share a window to explain what I'm trying to illustrate. Let me open a new window and I will explain. Okay, let me open a new window. Okay. Here we have our axis. Okay, let's say we have our point. Okay, for this point, which I denote by x0 sub 0 x1, let's say you have a point here for that one. You have another point maybe here, this. You have another point there for this one. You have another point maybe there for this one. You have another point here at this abscissor, and then maybe another one maybe here for that one. Right. Okay, cloud of point, 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 things like that. Okay, let's say that's what you have. And I will put the corresponding coordinates. This is the projection on the x-axis. You have the abscissor, this one, and here you have that one. The next point is this one, and then you have the following point, and then you have this one there, and you have the last point somewhere here. So those are the points. Now, if you are asked to represent this, okay, so this is a function that is known at this point, right? Let's say this is n x sub n, right? And you have the corresponding values here on the x-axis, on the y-axis. This one, for instance, this is y0. And you have all the other points there on that axis. Yn is this one, which is somewhere here. So you see that we have this set of points. We have this set of points x0, y0, up to xn, yn. Now, but this point, in fact, represents a quantity that we denote by a certain function f. Well, we don't know the function. We don't know the expression of this function. We only know the function at this discrete point. So f, the name of the function, f is known at discrete point, n discrete point. But we don't have an analytical representation of f. And the purpose of numerical methods is to find an approximation of that. That's approximation theory. So which expression can we use, or which function, or which type of analytical expression can we use to represent this set of data points? We know that we can use polynomial interpolation. As I mentioned earlier on, it's not a good approximation. Interpolation to polynomial. Now, for interpolating polynomial, the degree of the polynomial will be n. And as you know, the behavior of an interpolating of a polynomial will have turning points, like here. To move from here to there, that polynomial will have to turn. And this, around here, there will be a turning point. Similarly, all over. So the aptitude of the polynomial to try to adapt to pass through all the points will make it such a way that it will misbehave towards the end point. And that's where the error becomes very large. Right? And this phenomenon is called round phenomenon. Okay, let me try to represent that interpolating polynomial. If I try to represent, you will see that somewhere there will be very wide oscillation towards the end point, because that polynomial will try to pass through this point. It can come from the bottom, from below, or it can come from above, but it will be wide, because it will do that in order to pass through all the points. So we might have something like this, where the polynomial is really wide, and then it comes to go through, because remember that interpolating means that it passes through all the points. So the polynomial would do its best, he would try his best to go through that, and for that purpose, for continuity and differentiability, you see, a polynomial is continuous and is also differentiable. So you see, for differentiability, it has to be smooth, right? And for that purpose, the behavior will be horrible towards the end point. It might, something like that. It might see, you see that towards the end point, or it might be like that, or it might be like this. It will depend on the value of the function. Or it might go to, after that, it might go to infinity, something like that, because of all the curvatures and the bends and all that. So that is your interpolating polynomial, something like that. It can come from above, as I said, something like that. You see that, because you say interpolating, you have to pass through all the points. So that's a huge constraint on the polynomial. So which means that if you compute the error here, you see that the error in general will always be large. And the largest contribution will come from the end point towards here. But if, okay, let me leave that one. Now, if I use piecewise polynomial interpolation, so this is Pn, which is a polynomial interpolation. I call it Pn of degree n. Now, if you use piecewise, I can take piecewise of first degree or piecewise of second degree, meaning that in each subinterval, all right. This formula of Pn is a single form expression. This Pn can be written as, this is where you will see the difference. This Pn is a single polynomial, meaning that you can write this Pn as, for a particular x, Pnx will be written as a single polynomial with a single expression, k running from 0 to n, akxk. You have a single expression for this one. But for piecewise, you don't have a single expression for the polynomial. You have many. For each subinterval, you have a polynomial, which you can decide to be second degree, first degree, second degree, or third degree in each subinterval. That's what you call piecewise polynomial interpolation. And when the degree in each subinterval is 3, we call that a spline, a cubic spline. In fact, they are all called spline, but when n is equal to 3, we call it cubic spline. And you find cubic spline in most of the numerical method textbooks. In the beginning, I introduced those spline, cubic spline, but I realized that students were struggling, and I removed it. That's why you don't see cubic spline here. I removed that part because students were really struggling with that. But it's something that you need to know, right? I'm just saying it. You need to know what is the cubic spline, and that's why I am explaining that now. So if I use piecewise, I can decide that in each subinterval xk plus 1, I can decide that each polynomial will be first degree. Then you call it first degree piecewise polynomial. If in each subinterval I take a second degree polynomial to join these two points, you call it second degree piecewise polynomial. And then if it's third degree, we say that it's a cubic spline. Cubic spline. Okay. Now, if I use the spline, with the spline, the error is really minimized. Particularly, the best choice is the cubic spline. Why cubic spline? Because if I take first order polynomial, I will join each of these with a straight line. Let us do that. If I use a straight line, you can see this is what we have. And then in the second interval, that's what the polynomial will be. You have this polynomial, which is an increasing polynomial. Here you have a decreasing polynomial. You see that the polynomial here and there are completely different. Because I have a single polynomial in this interval, I have another single polynomial in the second interval, and so forth. So in each subinterval, I have a different expression of the polynomial. Whereas with Pn here, interpolating polynomial, I have a single expression for the entire interval. So that's the difference, and you need to understand that very well. So this will be, I will just glue all of them together to obtain the expression of this f. So it will be piecewise. In each of a subinterval, I have an expression. So that will be, so I will say here in red, I have, oh, sorry. So that's the second, first degree polynomial. Okay, now the drawback with this one, you can see that when I do this, I enforce continuity there, but differentiability is not. You can see here, the polynomial here, the function is not differentiable at those points. So there's no differentiability. But if the original function is differentiable, you see that that differentiability is lost already. Good. Now, from second degree polynomial, you know that with the second degree polynomial, there's curvature. But first degree, there's no curvature. That's why it's not smooth, right? It's not smooth at this point. At the interior point, you see that it's not smooth, right? But if I take a second degree polynomial, there will be smoothness, because second degree polynomial will capture curvature, right? And similarly with the third degree. The third degree will capture curvature, but you also capture in case you have turning, if you have a inflection point, a third degree polynomial can capture inflection point. So that's why cubic spline is much better compared to first degree and second degree polynomial. But the drawback is that you have to compute more coefficient for each polynomial in the subinterval. That's the only drawback. So let me draw the case of oh, they are similar. This is similar. Let me choose, okay, a different color. So this, the green will be P, P2, second degree. Okay, second degree. For a second degree polynomial, you need three coefficients. Second degree, you have A0, A1, A2, three coefficients. First degree, You have 2 coefficients. And then third degree, you have 4 coefficients. Okay, so second degree, you can have something like this. It will be closer because you can see that this is almost quadratic. So your second degree polynomial will capture this properly. It will be closer to that one. Oh, sorry. Yeah, I have to make sure. So that's the first one. And then second one, in the second subinterval, will also be something like this. No, you can see that this one is almost third degree. You can see that there's a turning point here. There's an inflection point. But second degree polynomial will not capture that. It will not capture the inflection point. It will not. The best a second degree polynomial can do at this stage, either it will go like this, because it's a parabola. It can, let me. The best a second degree polynomial can do will be this, something like this. So if you start from here, you can have something like that, like this. It has to be a parabola, or parabola from here, like this. That's for second degree. But if we assume that the original function has a behavior that is closer to the blue line, this one, the blue line, you see that we need a third degree polynomial to capture that behavior. Because for a third degree polynomial, it can easily change a third degree polynomial. Let me take this one for the third degree polynomial. This one, you have a turning point here. A third degree polynomial will capture that properly, like that. Oh, sorry. You see, a third degree polynomial can do that. So the bottom line is, if you want a more precise method to replace an interpolating polynomial, is a cubic spline. For the reason that I already explained, a cubic spline will do the job properly. And I refer you to the prescribed textbook. If you go to the section cubic spline, you have an idea. But it's out of the scope of our syllabus. Okay, so this is, I already explained the drawback. Now, when it comes to the least square method, what the least square method would do, it will just minimize the error. And by minimizing the error, you can use either a straight line or a second degree polynomial. Now, if you use a second degree polynomial here, it will be terrible, because a second degree polynomial will behave in one of the following manner. Okay, a second degree polynomial can be something like this. A parabola that will go like that and try to minimize, right? It might pass to some of the point or none of them at all. So this is a possibility, the one that I drew there. Let me erase that again. So you have that possibility. Or you can have something like this. A second degree polynomial coming. Oh, sorry. Or a second degree polynomial coming like this. A parabola, like that. Provided it minimizes, right? Those are the various scenarios. But the best in general is when I say the base, the commonly used will be a straight line. A straight line that, oh, sorry. A straight line that will go this way, it will be something like this. A straight line that will minimize the error. That. You see. Okay, so this is something that you know already. This is just a recall. So let's go back to okay, so let's go back to chapter 1. So we have the least square method, and this is a straight line that I already mentioned. We can use a polynomial of any degree to minimize the error. So that's the least square method. But where we will stress much in this in the approximation theory will be the rational function, because this least square method, you know what is the least square method. You already know about this, the least square method. That's why I will not spend too much time on that, on the least square. But where I will spend much time will be here. 1, 5, 1, 6, 1, 7, 1, 8. Rational function approximation per day, approximate method, continuous fraction, Chebyshev polynomial, Fourier series, and trigonometric polynomial. It will really take time to cover that. So because of that, and because of the scope of the syllabus, you can see we don't really have too much time to spend on least square method. So that's why I advise you to download this chapter, which I will upload, of course. I will upload it. Please go through, and by tomorrow, for those who join us late, I mentioned that by tomorrow I will also upload tutorial 1 so that you start solving problems and get acquainted with what awaits you during the test, because most of you, I know that you are just there to get the marks. You don't care whether you understand or not, which is not actually what it's supposed to be. I stress on understanding. Okay, so let us quickly go through. Before we go through, we move to the next slide. I was talking about the purpose of approximation theory. I mentioned the least square method. I mentioned also polynomial interpolation. We also have rational function approximation. With rational function approximation, the advantage here is also the error minimization, because if you contrast it to polynomial interpolation, here you have the ratios of two polynomials. A rational function is a ratio of two polynomials. And there is the Padé approximation or approximating method that we will tackle on the rational function approximation. We have the Padé. And the purpose of the Padé here is to find a rational function that will approximate the given function f that I mentioned earlier on, under some restrictions. Okay, then the next will be Chebyshev polynomials. Chebyshev polynomials will be polynomials of a certain kind, right? They are trigonometric polynomials, as we will see later on. They are a particular form of polynomial that we use to approximate the function f. And after Chebyshev polynomial, we will tackle Fourier series. And Fourier series is mainly important when it comes to things like digital signal processing. It has a lot of application in digital signal processing. It also has a lot of application when it comes to electrical engineering. Anything that is related to signal, electrical engineering. In electricity, you have signals. Even in computer science, right? Your computer, most of the bits that we manipulate in computers, these are signals. That's digital signal processing also. And this Fourier series has a lot of application in that regard. So, roughly speaking, that's what we will cover under the umbrella of approximation theory. In application, we'll see how it is being used in some of the application. As I mentioned, electrical engineering, digital signal processing, computer science, and the like. So now we can dive straight into discrete least square method. In the least square method, we have the set of data point, as I mentioned already, the set of data point xi, yi. You have your xi and yi. That is your data point. Now you want to represent it using an expression. This type of expression. This one, y equal to f of x. Now, if you write the formula for f of x, it can be a polynomial, it can be any function. Then you substitute x into the expression of that, and you try to minimize this error. Because this function f will depend on some coefficient, f depends so in general, this function f will depend on some parameter, a0, a1, maybe up to a something, let's say am. Now, in order to minimize this, we will minimize this with respect to these parameters. So we'll find the values of these parameters that will minimize the error. And for that, when we substitute, we will take this function s as a function of these parameters, a0 up to an. And to minimize the error, we will take the partial derivative of s with respect to the parameters and set that to be 0. This is what we call optimal condition. And by setting this, we will obtain what we call the normal equations, right? So this will lead us to normal equations. And this normal equation will give us the values of the parameters a0 up to an. And once we obtain the values of the parameter, we come back and substitute into the expression of f. So that is how the least square method works. And something that you saw in okay, this is an example here. If we take our function to be a line, you can see that f of x depends on the parameters a0 and a1. Right. Now, if we write this expression, the error expression, and we substitute here into s for the line, we obtain this. So you can see that s depends on a0 and a1. So if we write the optimality condition, partial derivative with respect to the parameter equal to 0. We enforce that 0. Right? The equation that we obtain is the normal equation, and these are the normal equation for a straight line. This can be easily solved for A and B because it's a linear system of two equations with two unknowns. So A0 and A1 will be determined in a unique manner. So if we solve this linear system, there are many methods. You can use a Cramer's rule. You can use yeah, that's even the easiest and for this case. So if we use the Cramer rule, this is the formula for A0 and this is the formula for A1. And as an application, if we have our set of data points given by this cloud, we can find A0 and A1 through this formula. So we compute the sum of xi squared for this expression. We do the same for y, x, xy, and so forth. Then we get all these values from the table and substitute in the formula A0, A1. We get this formula, these expressions, and substitute in the formula for y, which is the formula for the straight line, this one. So if you substitute A0 and A1 into this formula, for this set of data points, we obtain this straight line from the least square approximation. So this will be the least square approximant of this set of data points. So that's what we obtain. Please, for revision, I encourage you to do all this computation yourself. Right. Okay, so this is just a refresher. So for the least square method, if we replace our function f by a polynomial of degree n, we do exactly the same thing. Our s, which here we denote by e, depends on a0, a1 up to an. And now our f of x is a polynomial. So if we expand this expression, and then we perform, in fact, we impose the optimality condition, which is partial derivative of e with respect to the a sub j equal to 0 for j running from 0 to n. Now, for you to be able to differentiate this properly, you need to look at this expression and differentiate with respect to a sub j. Please, this is a homework. I encourage you to obtain exactly the same expression. Make sure that you are able to differentiate this expression with respect to an arbitrary a sub something. It can be a sub k, a sub something that you fix. You fix it, you come this formula, this expression 112, and differentiate it with respect to a sub j. I want you to be able to obtain this result. Don't just look at the result, but make sure that you can actually obtain the same result. You only learn by doing. Please, this is the first homework that I'm giving you. So, this expression from what? Okay, I think we'll stop here for today. This is not new to you. Huh? This is something that you did in MMO, right? So do this computation and read through what we will do tomorrow. Will be this MATLAB application. We are going to program this together tomorrow. And after that, we will dive straight into the case of the integral. I'm not sure you did the integral in MMO. I'm not sure, but I know that you did the polynomial, but I'm not sure about the integral. Right? I'm not sure that you use integral. I don't know. But you confirm with me, check and confirm with me tomorrow. If you did integral, we will skip. Otherwise, we will differentiate this formula together tomorrow, this one, the normal equation. We will do that tomorrow. And if there is enough time, I will introduce the rational function approximation. Okay, so we stop here for today. Is there any question before we part? Is there any question?
Doctor?
Yes.
Would you put the note on the MC or
I can't hear you properly.
I'm saying, would you upload that notes on the MC?
This chapter?
Yeah.
Yeah, I will do it.
All right.
I think I will do it right away. After this class, I will upload it. So check here on the platform, not on the e-learning, here on the Microsoft team.
Okay, okay.
Great. Okay, if there's no further question. Yes?
Doctor, not only the chapter, but you must also upload the video.
No, but the video will be here. It's always there.
Okay.
Yeah. After this class, the system will upload the video automatically. It might take a few minutes, no more than 5 minutes. The video will be uploaded. Please make sure that you download, because after maybe 2 weeks, the video will be deleted. Any other question? Is there any other question? Okay, so we'll stop here for today. Thank you for your kind attention. God bless you and see you tomorrow. Bye-bye.
Okay.